Hey guys, welcome back to my YouTube channel Tech Talks with AK. I'm Ankit Kumar. In this video, we are going to discuss about Big O and Big O notation. So first thing first, what is Big O? Big O is a notation used to classify how scalable an algorithm or function is, and it allows us to estimate the worst case runtime of an algorithm or how long it takes the algorithm to complete based on the input size. So what this means is that Big O informs us of how much slower an algorithm will run if its input size grows. If the input size gets larger, say an array of 100 elements instead of array of 50 elements, will the runtime of that function stay the same? Will the runtime get proportionally larger as the input size increases? Will the runtime get exponentially larger, or will the runtime change in some other way? This is what Big O notation tells us, and it describes how performant a function or an algorithm is. So let's do an example to help us visualize how Big O works. If we have a function called log that simply takes in an array and logs out first two elements of that array, what is its Big O notation or runtime going to be? The runtime of this function is going to be constant. That's why this type of runtime is called constant runtime, which we write as Big O of 1 in Big O notation. We know that the runtime is constant because as the input size increases, or in this case, if we increase the size of our array, this array, the number of operations that we perform never changes. We still log out only two first element no matter how large array gets. This is called constant runtime, and it is written as Big O of 1 in Big O notation. We can see this visualized on this graph. As the input size increases, the x-axis, the time it takes to run the function never changes, which is on y-axis. Let's do another example. Now we have a function called log_all, which takes an array and logs out every element in that array. What is the runtime of this function? Well, we know that we have to do an operation on every single element in that array now. So as the input size increases, our runtime will also increases for this function. Our runtime will increase proportionally to how much our input increases, and that makes sense, right? If our array has 5 elements, we will have to perform 5 operations or log it out 5 times. If it has 6 elements, we will have to perform 6 operations or log it out 6 times. If it has 7 elements, we will have to perform 7 operations and so on. This is called linear runtime because the runtime is proportional to the input, and we write it as Big O of n in Big O notation, where O stands for function and n stands for the size of the input. Let's run two more runtimes or time complexities that very often seen throughout the engineering and programming, and that we will come across in this video series. The next runtime that we will explore is exponential runtime. So now we have a function called add and log, which takes an array as input. What it does, it gives us every possible combination of pairs in the array, iterate through the whole array, but on every element it goes through the whole array and hits on the every other element again. So all possible pairs are made. That's why we have two nested loops here. So for example, if we have an array of 2 elements, then 4 pairs will be logged out. If we have an array of 3 elements, then all 9 pairs will be logged out. If we have an array of 4 elements, then all 16 pairs will be logged out. This is exponential. As we add one element to the input, the runtimes make an exponential jump. You can see this visualized on the graph, and you can tell that this is not very efficient or performant way. If you write a function like this in your code, you probably won't be able to notice the performance issue with very small inputs, but as your input starts to scale and becomes very large, a function with exponential time complexity becomes very inefficient and can slow down an application. So we try to stay away from creating functions that have this runtime as much as possible. An exponential runtime is written as big O of n square in big O notation. Now, the final runtime that we will explore is logarithmic runtime, and it's very performant. An example of algorithmic runtime is binary search. You can see the code for this over here. Instead of running through this code, let's think about it conceptually. In an binary search algorithm, we will have two inputs. One is a list that must be sorted in some way, either numerically from least to greatest or from greatest to least, or alphabetically has to be sorted in some way. And our other input is simply just a single value or key that we want to try and search for within our array. Binary search has logarithmic runtime because every operations that we perform, we are cutting the input in half. This is great because even if we have a huge input, we are only going to be looking at a fraction of elements to find the one that we are searching for. Let's take a real life practical example of binary search. If you had a physical dictionary and if you wanted to find a single word in that dictionary, you would find it by doing binary search, probably without even realizing it. Let's say that you are looking for word programming in your dictionary. You would open up the dictionary to the middle and you will notice that you are in the M section. Well, you know that programming will be after M section, so you can totally forget about the first half of the book or the dictionary. So we just cut our input size or the number of elements that we have to search through in half. We are now left with the second half of the book. So we will go into the middle of the section and we will notice that we are in now T section. We know that the word programming will be before the T section or T. So we threw away T and everything after it. So we just cut out our input size in half again. We are now left with section N through S. We go to the middle of what we have left and we end up in the P. And we have successfully found the word programming in the P. This is essentially binary search, and you can tell that it is efficient because we only performed about 4 operations to find out what we were looking for when our input had 26 elements. As our input grows, the number of operations that we'll perform will not grow proportionally, but it will grow logarithmically. If we had input size of 4000, it would take only around 12 operations to find the element that we are looking for. This is really powerful and really efficient. Binary search is an example of logarithmic runtime or time complexity, which is written as big O of log n in big O notation, and you can see it depicted on our graph here. That's it guys for our introduction to runtime and big O notation. In next video, we will wrap up our work with linked list by going over their performance and use cases. And we will explore their runtime for different operations like insert and search. That's all for this video guys. If you like this video, please press thumbs up, share with your friends who might find it useful, and don't forget to subscribe to get notified about more interesting technical videos from Tech Talks with AK. If you have any question, any feedback or any suggestion, please write down below in the comment box. Thank you.